There is a number that people have called the fingerprint of God. They say it is hidden in the Mona Lisa, in the pyramids of Egypt, in the spiral of a seashell, and even in the proportions of your own face. It is called the golden ratio, roughly 1.618, and almost everything you have been told about it is wrong. The seashell does not actually follow it. The Parthenon was not designed around it. Leonardo did not use it to paint the Mona Lisa. But here is the strange part. Once you strip away the myths, what is left is not disappointing. It is far more astonishing than the legend ever was. Because this single number turns out to be, in a precise mathematical sense, the most irrational number that can possibly exist. And that one hidden property quietly shapes the way flowers grow, the way leaves are arranged around a stem, and the very border between order and chaos. This is the real story of the golden ratio. So let us start with what the golden ratio really is, before anyone decided it was magic. Imagine a single line. You want to cut it into two pieces, a long piece and a short piece. There are infinitely many ways to do this, but there is exactly one special cut, where the whole line compared to the long piece is in the same proportion as the long piece compared to the short piece. When those two ratios are equal, the line has been divided in what the ancient Greeks called extreme and mean ratio. And that ratio is the golden ratio. Its value is 1.618033, and the digits never end and never repeat. Mathematicians call it phi, after the Greek sculptor Phidias, though he almost certainly never used it. Phi is not a rounded, friendly number. It is an irrational number, like pi. But as we are about to see, it is irrational in a way that no other number in the universe can match. Before we get to that, we have to deal with the legend, because the legend is everywhere. Walk into any design class, and you will hear that the golden ratio is the secret formula of beauty, that great artists and architects used it for thousands of years, that nature itself is built on it. So where did all of this come from? The story really begins in 1509, when a monk named Luca Pacioli published a book called The Divine Proportion, illustrated by his friend Leonardo da Vinci. Pacioli admired the ratio for its mathematics, but over the centuries, admiration turned into obsession. Then, in the 1800s, a German named Adolf Zeissing declared that this single proportion was the universal law of beauty, present in the human body, in plants, in art, in everything. He had almost no evidence, but the idea was irresistible, and once it took hold, people started seeing the golden ratio everywhere they looked, whether it was really there or not. And that is the trap. If you go looking for a number around 1.6, you will always find it somewhere. Take the Parthenon in Athens. People draw golden rectangles over its front all the time, but the rectangles never quite line up, and you have to choose exactly which edges to measure to make it work. There is no record that its builders ever used the ratio. The Great Pyramid, the same story. The numbers are close to several ratios, and close is not the same as chosen. The Mona Lisa? There is no evidence Leonardo used phi to frame her face. The rectangles are placed after the fact. And the famous nautilus shell, the poster child of the golden spiral? A nautilus really does grow in a logarithmic spiral, but its growth ratio is closer to 1.3, not 1.6. It is simply the wrong number. Almost every classic example of the golden ratio in art and nature falls apart the moment you measure carefully. So you might expect this video to end here, with the golden ratio exposed as a fraud. But it does not, because the real mathematics is only just beginning. Here is the question that matters. If the golden ratio is not the secret of the Mona Lisa, why does it refuse to go away? Why do mathematicians who love to puncture myths still call phi one of the most remarkable numbers ever discovered? The answer has nothing to do with art, or beauty, or ancient architects. It has to do with a rabbit problem from the year 1200, a strange, never-ending fraction, and a competition that plays out in every sunflower on Earth. To see it, we have to meet the man whose name became attached to the most famous sequence in mathematics. In the year 1202, an Italian mathematician named Leonardo of Pisa, remembered today as Fibonacci, posed a simple puzzle about breeding rabbits. Start with one pair. Every month, each mature pair produces a new pair. How many pairs do you have over time? Count them, and you get a sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Each number is simply the sum of the two before it. This is the Fibonacci sequence, and on its own it looks like a curiosity. But now do something surprising. Take each number and divide it by the one before it. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is 1.66. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. The further you go, the more these ratios close in on a single value, and that value is phi. The golden ratio is quietly hiding inside the rabbits. Why should a sequence about rabbits lead to this one specific number? The reason is a beautiful piece of self-reference. Phi is the one number that satisfies a strangely simple rule. If you square it, you get the same thing as adding 1 to it. Phi squared equals phi plus 1. Rearrange that, and you find something even more elegant. Phi equals 1 plus 1 divided by phi. Look at what that says. The golden ratio contains a copy of itself, inside itself, forever. It is a number defined in terms of its own reflection. This self-similar structure is exactly what the Fibonacci sequence is slowly building, step by step, as each new term folds the last two together. The rabbits were never really about rabbits. They were a machine for approximating a number that describes its own shape. And that self-referential nature is the doorway to phi's deepest and most surprising property. To understand that property, we need one of the most underrated ideas in mathematics: the continued fraction. Any number can be written as a whole part, plus 1 over another number, and that number can be written the same way, again and again, in a nested tower of fractions. This tower is like a fingerprint. It tells you how easy or how hard a number is to approximate using simple fractions. Numbers like 1/2 or 3/4 have towers that stop immediately. Even pi has a tower with big jumps in it, which is exactly why the fraction 22/7 is such a good, easy approximation of pi. Now watch what happens with phi. Remember, phi equals 1 plus 1 over phi. Substitute that formula into itself, over and over, and the tower never stops and never changes. It is 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 forever. The simplest possible continued fraction. Every single term is a 1. That endless string of ones looks almost boring. In fact, it is the most extreme fingerprint a number can have. Here is why. Those large jumps in pi's continued fraction are what let us approximate it well with a small fraction. The bigger the numbers in the tower, the easier the number is to pin down. Phi has the opposite. Its tower is nothing but ones, the smallest numbers possible. That means phi resists being approximated by any simple fraction more stubbornly than any other number in existence. You can get close, but you always have to work harder for phi than for pi, for the square root of 2, for anything. This is what mathematicians mean when they call phi the most irrational number. It is not a poetic phrase. It is a precise, provable fact. Phi sits farther from every fraction than any number can. And it turns out that this single, abstract property is the reason phi shows up in nature at all. Not in seashells or paintings, but in living, growing plants. Picture a plant growing from its tip. It needs to place new leaves, or new seeds, one after another, around a central stem. And it faces a real engineering problem. If it places each new leaf directly above an older one, the upper leaves will shade the lower ones from sunlight, and seeds will pile into wasteful gaps. To survive, the plant wants to spread each new leaf as far as possible from all the ones before it, so it rotates by a fixed angle before placing the next. But which angle? If it turns by half a circle each time, it only ever uses two directions, and everything lines up into two crowded rows. If it turns by any fraction of a circle, the pattern eventually repeats, and the leaves fall into a small number of spokes with big empty spaces between them. The perfect angle would be one that never, ever repeats, an angle based on the number that is hardest of all to express as a fraction, an angle based on phi. That angle has a name, the golden angle, about 137.5 degrees. It is a full circle divided according to the golden ratio, and because φ is the most irrational number, this angle never lets a new seed line up with an old one. Every seed finds fresh, open space. Turn seed after seed by the golden angle, and something remarkable appears on its own. Interlocking spirals winding in both directions, packing the seeds as tightly and evenly as physically possible. And if you count those spirals in a real sunflower, you get numbers like 34 one way and 55 the other. Fibonacci numbers, the very sequence that approaches phi. Now compare that to a rational angle. Turn by a simple fraction of a circle, and the seeds collapse into a handful of straight arms with gaping voids between them. A terrible way to pack a flower. The plant is not doing geometry for beauty. It is solving a packing problem, and the most irrational number is the best possible solution. There is one more place phi lives that is not a myth at all, the humble five-sided shape. Draw a regular pentagon, then draw its diagonals, connecting every corner to make a five-pointed star inside. Measure a diagonal of that pentagon and divide it by the length of a side. The answer is phi. Exactly. And it does not stop there. The lines of the star cut each other into pieces, and every one of those pieces relates to its neighbor by the golden ratio again. Inside the star, a smaller pentagon appears, holding a smaller star, which holds a smaller pentagon, endlessly, each one scaled by phi. This is why phi feels so alive. It is not just a value. It is a rule for self-similar growth, written into the geometry of five-fold symmetry. The same symmetry you find in starfish, in flowers, and in certain crystals that were once thought impossible. The people who chase this number read like a roll call of mathematical history. Around 300 years before Christ, Euclid wrote the first careful definition of it in his Elements, calling it, without any drama, the extreme and mean ratio. No mention of beauty, no mention of the divine, just clean geometry. Almost 2,000 years later, the astronomer Johannes Kepler fell under its spell. He wrote that geometry holds two great treasures. One is the theorem of Pythagoras, and the other is this very ratio. He called the first a measure of gold, and the second a precious jewel. It was Kepler who first clearly connected the Fibonacci numbers to phi. And yet, the name we all use, the golden ratio, is surprisingly modern. It did not appear until the 1800s. For most of its history, the world's most hyped number did not even have its famous name. So step back and look at what phi really is. It is not the secret of the Mona Lisa. It is not a magic rectangle for perfect design. It is something stranger and, honestly, more beautiful. Phi is the number that lies as far as it possibly can from every simple pattern. It is the mathematical definition of the most stubborn, least repeating quantity there is. And precisely because of that, nature reaches for it whenever it needs to spread things out without ever letting them collide. Sunlight on leaves, seeds in a flower head, florets in a pine cone. The golden ratio is not a symbol of order at all. It is the perfect balance point between order and chaos. Regular enough to build a pattern, irregular enough that the pattern never traps itself. That is the real treasure Kepler saw. Not a rule for beauty, but a rule for growth. The myths about the golden ratio were never the interesting part. They were a shadow cast by something genuine. Strip away the false claims about paintings and pyramids, and you are left with a number that defines the very edge of irrationality, that emerges on its own from a medieval rabbit puzzle, and that lets a flower solve a packing problem it could never calculate. The truth was hiding under the legend the whole time, and it did not need the legend to be extraordinary. Every animation in this video was coded by hand, line by line, to show these ideas the way they deserve to be seen. If watching the real mathematics unfold was better than the myth, consider subscribing, so the next number can tell its story too. Because reality has better secrets than the ones we invent for it.